My name is Alexander Isenko and I'm working as a PhD student at the Technical University of Munich. I'm the corresponding author of the paper that I will be presenting today, which is titled "Where is my training bottleneck? Hidden trade-offs in deep learning preprocessing pipelines." So first, I need to explain a bit of the background so we are all on the same page. When we talk about a deep learning training pipeline, we start with a dataset, which is followed by the preprocessing steps that transform the data to fit the model inputs. And finally, we have the training process that ingests said prepared data and then trains the model. Now, as we are focused on the preprocessing, this process can also be divided into multiple steps. Furthermore, these steps can be computed in two ways, either in an offline or online fashion. Offline processing means the steps are performed before the training has started and are saved to an intermediate storage, for example, a local SSD. Online processing means that it is running in parallel to the training, so the data is read from some storage and then fed directly to the training process. This architecture also features multiple throughputs, which we are interested in, that happen everywhere where data is read or written, namely T1 to T4. However, we mostly focus on the T4 throughput because we can compare it to the ingestion rate of the training process to see if we actually provide enough data to saturate its needs. And lastly, we call the decision where we split the preprocessing into an offline and online part a strategy. So, to motivate the problem, we have prepared the following example. This figure features the throughput of different GPUs for the popular ResNet 50 computer vision model. On the x-axis, you see the GPUs sorted by their compute capability, and on the y-axis you see the throughput in samples per second on a logarithmic scale. It's easy to see that with a better GPU, you get a higher throughput of the same model, even ranging to 1,000,000 samples per second for the TPU v3. Now, we profiled a simple CD preprocessing pipeline based on the ImageNet recognition challenge from 2012 and got the following results with 8 threads. When we were profiling the fully online strategy, that means preprocessing the entire dataset from scratch, we get a throughput of around 107 SPS, which does not saturate any of the GPU's ingestion rate. However, this also might not be very surprising, because why should we not save CPU cycles by caching the fully preprocessed dataset? We might improve the performance as we will only rely on the read speed of the storage. And with this, the fully offline strategy, we get an improvement to around 580 SPS. This is close to 6 times faster and finally saturates at least the T4 GPU. However, with our proposed strategy, which splits the pipeline somewhere in between, we managed to achieve a throughput of approximately 1,800 SPS. This supports 3 more GPUs, the A10, the A30 and the V100, all while staying on the same CPU hardware. Now, one might say that we argue in bad faith here, as we do not compare the other significant trade-off, which is the storage consumption. However, here too, we actually take 3 times less storage consumption compared to the offline processing, while being 3 times faster. So, I hope this was enough of a motivation as to why we focus on this topic, so let's introduce our contributions. First, we analyzed 7 representative preprocessing pipelines in total. We targeted 4 different domains: CV, NLP, non-intrusive load monitoring, abbreviated by NIL, and automatic speech recognition, abbreviated by ASR. We summarized the problems and the unexpected findings from the storage consumption and throughput trade-off, how well compression can speed up the pipeline, how well parallelization works in practice, and how caching affects the throughput and how it can be used to detect bottlenecks. Finally, we present Presto from Preprocessing Strategy Optimizer, an open source profiling tool that helps you automate the performance tuning based on the TF data framework. So let's jump into our first insight, which is fully offline preprocessing is not necessarily the best performing strategy. Our motivation was an example of this, which features the following CV pipeline. First, the files are concatenated, that means going from multiple image files to binary shards to remove the random access penalty. Then the images are decoded, meaning from the JPEG compression to an RGB matrix. Then they are resized to a fixed resolution. And finally pixel centered, which transformed each pixel to the range from -1 to +1. The last step, called random crop, is marked with a dotted line because it is random in every epoch and thus it just cannot be materialized and saved to disk. So let's take a look at the profiling results. The x-axis on this figure shows the strategy, meaning up to which and including step was the pipeline executed offline. On the left y-axis, you see the storage consumption in megabytes, but it is also featured above each bar. And on the right, you see the throughput in samples per second, which is shown with the dotted line. So let's start from the left. The leftmost strategy, unprocessed, also known as fully online processing, as you already know, is the slowest of all, with around 100 SPS, and it takes up the initial 146.9 gigabytes. Then, the next one, the concatenated strategy, already shows quite a big improvement in throughput to around 1000 SPS, just by removing the random access penalty. And its storage consumption also only changes marginally because of the metadata of the TF record format. The next one is the decoded strategy, which is the first throughput decrease to around 700 SPS. That is coupled with a big increase in storage consumption. This is interesting, as JPEG decoding is typically a slow step. However, caching it does not seem to improve throughput. And the reason for the slowdown is a multifaceted one, due to each sample now being almost 6 times larger. So first, the network bandwidth is used more, and second, the CPU just has to process that much more data. And these two things combined invalidate the time saving from not decoding the JPEGs, which was not very intuitive at all for us at first. So we looked into the slowdown and found out that our network bandwidth was not the problem this time, so it had to be a compute bottleneck. And to test this, we doubled the thread count and actually got a slightly improved throughput by around 140 SPS. While this helps a bit, just throwing more compute at an inefficient strategy does not really improve performance significantly. And this leads us to our proposed strategy for this pipeline, namely resized. The throughput is around 1800 SPS, and that is again also achieved by two things. First, we reduce the storage consumption by 2.5 times, which is always beneficial. And second, it caches one more additional preprocessing step in the pipeline. And these two things combined will always create a net benefit, as both potential bottlenecks are alleviated. The network bandwidth, because of the reduced storage consumption, and the CPU, because we cache one more additional step in the preprocessing pipeline. So yeah, and this actually results in the final strategy, namely the pixel-centered one. And we see there that only caching the following next step is not always favorable. This actually resulted in the second worst throughput of all, just because the storage consumption was increased to 1.4 terabyte. The reason for that is the normalization that changes the data type from int8 to float 32s, meaning from an 8-bit representation to a 32-bit representation for each pixel, which of course increases storage consumption by 4 times. So even caching up to the last possible step may actually not be beneficial if the storage consumption increases by such a big factor. So let's summarize our findings. When designing a preprocessing pipeline, try to look for steps that minimize storage consumption. The naive but powerful takeaway is this: the smaller the data gets, the faster you will be able to process it. So let's take a look at the next insight. Native implementations are not necessarily the best. To understand this, we take a look at the NIL pipeline, which works with high-frequency electrical signal data. The pipeline itself is actually quite trivial, as the data is decoded from files into tensors and then aggregated over its period length. The aggregation is comprised of multiple steps, like the root mean square function, over different electrical features like active power. The figure itself shows the speed up from 1 to 8 threads for each strategy. And the first thing to notice about this figure is that the very first two strategies seem to degrade with more threads, which is unusual, so they get slower. This stops at the aggregated step, but there is no effective speedup visible from there as well. So what happens there? So because we did not see this issue with other pipelines, this had to be something more implementation specific. This pipeline was actually the only one which used the proposed alpha code to preprocess the data by doing a NumPy call. So maybe this external function call outside of TensorFlow was somehow responsible for this performance. And to test this assumption, we generated a synthetic dataset of a total of 15 gigabytes and compared both the NumPy RMS implementation as well as the native TensorFlow one on the speedup. And on the x-axis of both plots, you see the different sample sizes of the synthetic dataset. And as you can already see, these results are heavily in favor of the TensorFlow implementation, as the NumPy one shows exactly the same characteristics as our NILM pipeline, meaning they degrade over time with more threads, while the TensorFlow one scaled pretty well with the thread count. However, when comparing the actual runtime of these two implementations, the NumPy RMS one takes 11 minutes in total with one single thread, while the TensorFlow one actually takes 32 minutes with 8 threads. So the reason for the bad scalability on NumPy is probably due to the Python global interpreter lock, while the inefficiency of the TensorFlow operators might just be something very framework specific that has to be tested on a case-by-case basis. So summarizing, just looking at parallelization capabilities is not enough when maximizing throughput, nor using only native implementations under the assumption that they are optimized efficiently. But what about the performance of the last strategy, aggregated? We only read data from disk without processing, so why don't we get at least a little bit of a speed up when reading with multiple threads? And this leads us to our last insight. Insight number 3. Small sample sizes can negatively affect performance. The NILM pipeline from the previous slide did not saturate our 10 gigabit network, and there is no obvious compute bottleneck left, as we just read from storage. So when we were looking for the issue that prevented the multi-threaded read speedup, we noticed one particular issue. All the pipelines which showed a bad speedup also had a small sample size, and to test this assumption, we reused our synthetic dataset and checked its multi-threaded read performance. On this figure, you can see on the y-axis the speedup for 8 threads and the different sample sizes of our synthetic 15 gigabyte dataset. Remember, we only profile reading from disk, so no actual preprocessing happens here. And the results show that the small sample size does indeed prevent a multi-threaded speedup, which was exactly the same case as with our NILM pipeline. So, for example, the 20 megabyte samples had a speedup of almost 6 with 8 threads, while the 0.01 megabyte samples were close to having no speedup at all. And the main reason for this degradation is probably due to the inefficient deserialization of every sample, which is followed by a context switch. The smaller the sample size, the more samples we have, which again leads to more context switches and in turn leads to worse performance. So to further validate our finding that this has nothing to do with the network bandwidth, we use 2 types of caching and profile the last strategy of every pipeline that fit into our memory. And this table shows the speedup to our no cache run for each pipeline, as you can see in the leftmost column. So going to the right, the system level caching means that we did not clear the cache manually after every epoch. So this is kind of the default way when you run a pipeline with a dataset that fits into your memory. And the application level caching means that we instructed TensorFlow specifically to cache the dataset. As you can see, with the NILM pipeline, actually has the smallest sample size of 0.01 megabytes, and it has almost no speedup compared to reading from disk, which is very bad if you compare the read speeds of an SSD versus local memory. On the other hand, the FLAG pipeline, which is one of the automatic speech recognition pipelines, has a sample size of 0.4 megabytes and is already 8 times faster when reading from application level caches compared to reading from disk. So, summarizing, this further validates our assumption that small sample sizes affect the read performance of TensorFlow negatively. And additionally, you can also see the major difference of system and application level caches in this table, which is also one of our many other insights which we talk about in the paper. So, concluding, we presented some of our findings which were created with Presto, an open source library that can help you to automatically find the best performing strategy. If you take away one thing from this presentation, it should be the following. Please do not underestimate the necessity of optimizing your preprocessing pipeline. Use our tool and many others to profile your deep learning pipelines, as there are many opportunities for a speed up without paying for additional hardware. To actually motivate you to read inside our paper, here's a glimpse of the insights we did not talk about. For example, how to correctly order preprocessing pipeline steps, when can compression reduce storage consumption and increase throughput at the same time, when does keeping dataset as PNGs actually saves storage consumption compared to JPEGs, and how caching can be used to expose CPU-intensive steps. Thank you very much for your attention, and please contact me if you have any questions regarding our research. Bye!